Hello Info-Person, this is Anton, and let's discuss dark matter once again. But in this case, actually a really exciting new experiment that maybe possibly kind of sort of found just something. Now nobody is saying it's dark matter yet, but it did find something. But in order to understand exactly what this experiment referred to as qrocodile is all about, and how everything was discovered, let's discuss some of the basics first, and let's find out what the international team behind the study recently achieved. As always, all of the links and all of the studies should be in the description below. But first the basics. And so for decades now, scientists have been trying to figure out exactly what this dark matter phenomenon is. We know it's there, we see the evidence for it everywhere, but nobody right now can explain what's causing it and why approximately 85% of all matter is essentially invisible. Obviously, we've had propositions in regards to maybe different formula, trying to rework cosmological models, or even trying to rework gravity itself, but the fact is still there. We know that something out there, approximately 85% of all mass, seems to produce these very bizarre effects. But to date, as of 2025, or I guess 2026 almost, so far there's only been some evidence, but nothing conclusive, and nothing that can definitively tell us what's happening. Right now we can only infer its existence through gravitational effects, such as for example gravitational lensing, and through the existence of massive galactic structures and cosmic structures that cannot be explained without the existence of dark matter. And so this is why this particular experiment was designed. As I mentioned, this is called qrocodile, Quantum Resolution Optimized Cryogenic Observatory for Dark Matter Incident at Low Energy. Or just to rephrase this, observing dark matter particles with extremely small mass. And what they've done in this case is quite remarkable. This is actually a really cool experiment and a really cool setup. And a setup that can be used not just for searching for dark matter, but also for a lot of other stuff. We'll be discussing this very soon. But why this setup, and how is this different from anything else? Well, the thing is, when it comes to the dark matter, scientists cannot even agree on what we should be looking for. So is it some kind of a really massive particle, which is sometimes referred to as WIMP, weakly interacting massive particle, which would require some kind of a large detector using relatively heavy atoms? Or is it something super tiny and not massive, and possibly even acting as a wave more so than a particle? The idea we've discussed previously in one of the videos in the description referred to as an axion. So essentially here there is no agreement, but so far some of the previous research, for example looking for WIMPs with experiments like Xenon, basically discovered nothing. Here this involved giant tanks of noble gases and cryogenic crystals, resembling something like this, that would essentially try to discover invisible particles through occasional collisions and the production of electrons. But after several decades, still nothing. But that doesn't mean that dark matter doesn't exist or that it's not real. It just means that it seems to exist across an incredibly large possible range of masses. It could be really small, it could be really big. And so it's really only in the last few years that researchers started to consider light particles. Particles with masses way below typical weak scale, and particles much lighter than anything we're used to detecting. But obviously this creates a problem. If a particle is so tiny, it can only transfer energy and thus be detectable when it hits ordinary matter that's also light. Basically, if it hits an atom that's really large, it's not going to budge it at all, and so it's going to be impossible to detect it. And so even dark matter detectors with lighter particles still had a major limitation to detecting some of the lowest possible particles. And that's because the maximum energy of transfer in this case would be extremely tiny. And so to detect something really small, or I guess something very low in energy and mass, you would require some kind of an experimental setup with an energy threshold below a single electron volt. And that's actually super low. Just as a comparison, a typical WIMP is believed to have energy or mass at least 1 billion times higher. And so this challenge motivated a lot of different teams to try to discover new techniques and basically create new detectors, and actually a whole new generation of experiments, by trying to use advanced sensors and advanced technologies that today are actually mostly used for quantum computing. Because here these technologies do allow us to achieve extremely low thresholds. And in a nutshell, this is what this qrocodile collaboration is all about. A team led by researchers from University of Zurich designed a very specific and relatively simple system in order to try to discover these low-energy particles. And here they use something known as SNSPD. This is basically the core of this experiment. You can read about this in one of the wiki articles in the description, but these are known as superconducting nanowire single-photon detectors. And well, for the lack of better words, think of this as a kind of a delicate electronic spider web. It's made of really tiny superconducting microwires, in this case containing tungsten silicates. And this is a really small device. Here the active layer is only approximately 2 nanometers thick, and this whole sensor is only about 600 by 600 micrometers. So it's basically not even visible to the naked eye. And well, as the name implies, these superconducting nanowire single-photon detectors are essentially meant to detect single photons, mostly in the optical and the infrared range. And so their actual purpose is to enable quantum optics and optical quantum technologies by allowing individual photon detections in various quantum computers. Today they're actually used in research on quantum key distribution, optical quantum computing, LiDAR, and even deep space optical communication. And we've discussed at least some of these studies in one of the videos in the description. But their main strength is extremely high detection efficiency, even in extremely dark conditions involving practically no photons. So they can literally detect just one single photon without producing major errors. But in this experiment, to make this work, the entire detector also had to be in extremely cold conditions. This was cooled down inside a cryostat and involved temperatures of just 100 millikelvin. Basically almost absolute zero. And the overall principle was pretty simple. If there's some kind of a dark matter particle, which might be moving through space at about 1/1000th of the speed of light, it may hit one of these superconducting materials and then deposit a very tiny amount of energy, which is going to create an extremely small nudge, causing the entire sensor to momentarily lose its superconductivity. And this would produce a detectable electrical pulse. And so it was really this low threshold that made this device so interesting. Here it allows us to detect dark matter particles with masses as low as 30 kiloelectron volts. So maybe not as low as some scientists are hoping for, but definitely so much lower than previous experiments. But because this was an experiment, they essentially then decided to see what could be discovered in approximately 415 hours. And so by trying to minimize outside light sources and by trying to block any possible optical paths, here the team performed a science run lasting 414 hours. And during this run, the experiment did make some significant discoveries. Although I guess the most important discovery is really the fact that it even worked and that it was able to detect something. But essentially here this experiment managed to explore a new difficult to reach area of energy where physicists always had trouble. And so by achieving this unprecedented low energy threshold, here scientists think that we can eventually place a new constraint on how light dark matter particles could be. And so for dark matter researchers, this narrows down possibilities. And so overall this shows us that these dark matter particles, if they exist, definitely cannot interact with ordinary matter as strongly as some of the previous theories suggested. Here researchers only observed very weak interactions. But as I mentioned, the experiment also discovered at least a few unusual signals. And so here, over the course of this 400-hour run, there were at least 15 individual, non-periodic pulses, which at the moment do not have an explanation. But right now it would be impossible to determine exactly what caused them. Basically, it could be dark matter, but it could also be something entirely different. And right now there is no claim that dark matter was actually discovered. As a matter of fact, these pulses may even stem from a lot of unwanted sources such as cosmic rays or even surrounding radioactivity in the location where this experiment was performed. And that's because this was performed above ground and not underground. And so the next obvious step in this case would be to perform the experiment again underground, where it would essentially be shielded from all of the cosmic radiation. But nevertheless, these 15 signals are still kind of interesting. As a matter of fact, for all we know, maybe all 15 were dark matter. But there's actually another really interesting feature in this experiment that can change everything. In this case, it's referred to as directionality. And so here, because this also has directional sensitivity, since Earth is moving across space and since it's orbiting the Sun and the Sun is orbiting around the galaxy, as we move across space, we actually expect different number of dark matter particles to hit us at different times. This is sometimes referred to as dark matter wind and was potentially discovered like a decade ago from one of the Italian experiments, but it was just never really confirmed. As a matter of fact, it was quite a contentious and somewhat controversial discovery, mostly because a lot of similar experiments seem to have actually seen nothing. Either way though, because this is such a sensitive detector, and because it involves a very thin layer geometry, this allows the researchers to actually establish directional preference. So basically, literally by moving the experimental setup and by either tilting it this way or that way, it becomes possible to detect this dark matter wind. And so here, if the detection rate changes depending on the way the detector is oriented, it may give us a very strong indicator for the presence of dark matter. So like, for example, if you tilt this and suddenly instead of 15 signals you get like 100 signals, this will be a huge discovery, and it will be a discovery of something groundbreaking. But unfortunately, as it stands right now, these 15 signals don't really tell us much. It's not enough to leverage this powerful directional tool, and it's not enough to make any conclusions. As a matter of fact, right now scientists think that all of this was just some kind of an isotropic background. So basically kind of like cosmic radiation, cosmic rays, and so on. Nevertheless, it's really the setup and the capability of this experiment that's the biggest discovery. And so here, this qrocodile may one day help us discover something really unique and something that scientists have been looking for several decades. And in this case, leveraging a tool that's already used in a lot of different experiments, but mostly focusing on quantum computing. But along with other experiments using various gas cylinders, cryogenic crystal detectors, or gas scintillators, this qrocodile serves as a very important reminder that this is an ongoing global effort. An effort to figure out exactly what we're missing in modern physical models, and an effort to try to discover this very important but still missing piece of the puzzle. The super tiny but influential particle that seems to be everywhere in the universe. And so, along with all of these other experiments, such as this one, Axion dark matter experiment, that's been going on for a pretty long time as well, here this new experiment fits in just the right way. It seems to tackle extremely difficult to find low mass dark matter particles that a lot of previous experiments could not possibly find. And so here this first run, despite being relatively short, definitely demonstrated that this technology seems to work. And the team behind this is already planning the next stage, and they decided to call it Nile qrocodile. In this case, Nile stands for Next Incremental Low Threshold Exposure. Basically, they're planning to go underground to shield us from the cosmic rays, but will also try to lower the threshold of energy, allowing scientists to discover even lower mass particles, with the most important next step being making this bigger, basically creating larger arrays and allowing for a larger area of detection. And so here, by conducting this experiment several times, and by importantly trying to vary the inclination or the tilt, it may one day become possible to see if there are some unusual particles with low mass after all, and if maybe they could be dark matter after all. Either way, this experiment definitely pushes the boundaries for research, but is also paving ways for the formation of these extremely sensitive quantum machines, or quantum sensors, able to detect minute deviations or minute particles even with extremely low energies. But exactly where all of this goes, only time will tell. Well, anyway, we'll definitely come back and discuss this more if there are some additional discoveries. Until then, check out some of the previous dark matter videos in the description below. Thank you for watching, subscribe, come back tomorrow to learn something else. Support the channel on Patreon where you can find additional videos without any ads and can DM it directly, or by joining a channel membership that grants you early access. You can also buy the wonderful person t-shirt in the description below. Stay wonderful, I'll see you tomorrow, and as always, bye bye.